I will. Thank you, Harold. Good morning. It's my pleasure to introduce our keynote speaker for day 2. Dave Doyle is joining us this morning. Dave joined the National Geodetic Survey in 1972 and held the position of Chief Geodetic Surveyor for 12 years prior to his retirement in January of 2013. He was responsible for the development, technical design, and management of plans and programs that enhance the United States National Spatial Reference System. During his career with the NGS, his experience included all phases of geodetic triangulation, astronomic positioning, leveling, GPS data collection, data analysis, data transformations, network adjustments, data publication, and outreach in the form of seminars, workshops, and webinars. His efforts also included extensive activities to direct and coordinate the modernization of the National Geodetic reference frames in the countries of Africa, in countries in Africa, Central America, the Caribbean, South America, Eastern Europe, and the Pacific. Mr. Doyle is past president of the American Association for Geodetic Surveying, a fellow member of the American Congress on Surveying and Mapping, and has served on the U.S. delegation to the International Federation of Surveyors. He is also an active member of the District of Columbia, Maryland, and Virginia Professional Surveyors Associations. With that, please welcome Dave Doyle. We're going to jump on the screen.
Well,
I think it'd be good.
good.
Thank you,
sir.
Dave.
Thank you. What a pleasure to be here. My only problem with a session like this, 30 minutes, my friend Chris Berglund, sitting in the back there from Blue Marble, Chris will tell you, for me personally, this is my version of Dante's Ninth Circle of Hell. You know, having only 30 minutes to talk about what I am so passionate about. Look, here's the deal. I've got this thing titled, This Modernization of the National Spatial Reference System. Okay, thank you. Looking at the dynamics of positioning in a new environment. It could just as easily, I could have easily named it, How to Know Exactly Where you Are and Be Totally Lost. One of the things that we've certainly encountered, I certainly encountered in my career, particularly over the last 30 plus years with the development of the global positioning system, so many people looking for incredibly high levels of positional integrity, a centimeter. And I hope no one here is metrically challenged as I speak metric. So everybody's looking for a centimeter, and you buy boxes that will give you a centimeter. You can go anywhere on the planet and position themselves within roughly about 1 to 2 centimeters. And yet, so often what we find is, I have a centimeter, you have a centimeter, and our centimeters look like this. They don't match, oftentimes by many meters. Why? Well, the reality is that, unfortunately, we have so many people involved in high accuracy positioning. And it is the foundation of everything you do in a GIS. I don't care what venue you come from, what perspective you're using GIS for. Your coordinates and heights are the foundation of everything you're trying to put together. Now, if you live in a world where your positional integrity is 2 or 3 meters, have a nice day. You know, you're done. out of here. Most people aren't like that, and increasingly the demands are higher and higher. The National Geodetic Survey, where I worked for 42 years, is in the process of redefining the entire coordinate system for the United States, both height, positions, and heights. This is going to come about on roughly January the 1st, 2022 is the target, assuming that the budget stays the same. So I want to introduce you, in the short time that I had here this morning, I want to introduce you to this process, what's going to happen, what's going to be the impact. So let's take a look at this. Let's see what's going on. It's not working. Okay. So here we go. Uh-oh.
Can you get the
Okay.
TVs as well?
Yes, sir.
Thank you.
All right, got it. So let me introduce you to the National Geospatial Reference System. This is the collection of spatial data, positions, heights, that have been formed by the National Geodetic Survey, have been developed by the National Geodetic Survey over its over 200-year history. The National Geodetic Survey holds the legacy of being the oldest science agency in the federal government, created by Thomas Jefferson in 1807. Excuse me. So that happens when you get old. The bottom line is that it provides the foundation for accurate positioning, latitude, longitude, or northing and easting if you work in state plane coordinates or UTM coordinates, and heights. Those are the key elements that most people are looking for. It's three elements, scale, gravity, and orientation, that are the requirement that NGS has to deliver that. And increasingly, this is the key part, increasingly, this, how things change with time. I just want to leave a question out there. I'll come back to it here in a few minutes. What you think about it? Obviously, I don't want anybody to raise their hand. Anybody know how fast we are moving on the North American tectonic plate where we are right now? Think about it. We'll come back to it. We know what this is now. This is really cool stuff. Right? We are on the cusp of some major advances in positioning technology. When I joined NGS in 1972, I had come from a 3-year stint in the Army as a geodetic surveyor. And one of the things that I found almost instantaneously is that the agency was playing catch-up to electronic positional technology, and has continued to do so ever since because the changes have been so fast. We've come to a point, or we had come to a point, where we sort of felt like we were relatively stable. But we know some things are going to happen. We know some things are going to change in the next few years. So NGS, when I was still there as Chief Geodetic Surveyor, we put together a plan that identifies what needs to happen. And this will have an impact on every community in this country that holds any amount of spatial information. And that's monumental today compared to years ago. One of my functions back in the early 70s, I was on the management team that designed and implemented the North American datum of 1983, which is the horizontal datum for the United States right now. And one of my functions was to go out in the public and help institutions migrate from the older datum to the newer one. And what I very quickly found was that the overwhelming majority of users of data were really pretty small. A few feds, U.S. Geological Survey, Corps of Engineers, a few state DOTs. That's pretty much about it. There was really almost no one that had any significant amount of high accuracy data. So it wasn't a really hard job. In very short order, all of that has changed. The development of geographic information systems, along with the implementation of the global positioning system, has been like a perfect storm in all of this. If you step back in time, Mark and I were talking about this last night over dinner, the early days of GIS, which we were both involved in, everything being done on punch cards, referred to as computer mapping. Well, the reality now is it's in a handheld, it's in a tablet, it's so easy. Almost, if you have the IQ of a squirrel, this is something you can do. The same is true on the positioning side. But now we're challenged with understanding the fundamentals of how all this is held together. This National Spatial Reference System, while it has many different components to it, I want to introduce you to just the two that are the most prevalent and important in the aspect of positioning. And at least up front, you're probably familiar, at least at some level, with this. Some network of passive survey monuments. And they come in many sizes and shapes. These are just some of my favorites. Poured-in-place concrete post with a brass, bronze, or aluminum cap in the top, or a stainless steel rod driven to refusal. Some others that are my favorites, this little chisel square was the primary benchmark to determine heights for the United States in 1877. Still there. It's in Hagerstown, Maryland, not too terribly far from here. I particularly like this one, granite pillar. It's down on the Outer Banks. If you ever go down to the Outer Banks in North Carolina, it's right there. 1848, monument was established as part of the foundation, the early foundation of this. And I put these pictures up because this is how, historically, coordinates and heights have been delivered, have been realized, is the term we like to use. So if somebody needed accurate coordinates, latitude, longitude, state plane coordinates, UTM coordinates, or good height, they had to go find something that looked like one of these, that someone else, some authoritative organization, had performed a survey of some high contact and provided that information to. So A, it means you have to know where these things are. You have to visit them. That means you've got to put somebody in a vehicle. You have to give them a toy. And they have to go down the road to find them. And regrettably, there's a class of subhumanoids known as grader operators. And their whole function in life is to do nothing except tear these things out. It's true. Trust me on this one. The advent of space-based positioning has allowed us to move forward from passive control. Because if I determine a position or a height for one of these, and then I walk away from it, I have no idea how good that position or height is anymore. Once I go around the corner, I'm out of touch with it. Is it subsiding? Is it uplifting? Has somebody moved it? I don't know. There are over 1 million of these in the National Geodetic Survey's database that they provide to surveyors and others around the country. The integrity of them anymore? We don't know. We don't know because they're not commonly reobserved, reevaluated. Today, we now have a new capacity. Continuously operating reference stations, CORES, is the working acronym here. Wonderful. Dual frequency GPS mounted on a very stable platform. They operate 24 hours a day, 365 days a year. Some collect information every 1 second, 5, 15, or 30 seconds. So if one of these things moves, we pretty much know about it within literally almost instantaneously. We've had a number of occasions when I was still at NGS where there would be an earthquake, obviously in California and places like Alaska, where we could watch these stations actually walk, looking at the plate tectonic motion. So today, our capacity for delivering, for realizing our horizontal and vertical coordinate systems is no longer through these passive marks, although they're still there, and people do still use them. It's now through active control. And through this active control, I no longer have to go and visit them. In fact, in many cases, you can. It might be up on top of a building somewhere. It might be in a secured location. Many of them you can. This one, I know this one very well. Anybody here can go and visit it. It's at an NGS facility just outside Fredericksburg, Virginia. But if you go there, you're kind of like, okay, so now what? You don't do anything to it. You don't take that receiver off and put yours on. You don't do anything to it. You go to wherever you need the observations. You use dual frequency or even single frequency GPS, and there are a variety of ways in which the data can be processed. Actually, the National Geographic Survey has a wonderful tool, and if you're not in the field, it may not mean anything to you, but it's a tool called OPUS, the Online Positioning User Service. If you go out with a dual frequency receiver, set it up anywhere in the world, collect data for roughly about 2 hours, submit that data to NGS, and within 5 minutes, NGS is going to send you back a data sheet that says this is where you are. Any of you coordinates and heights, anywhere in the world, and especially in the US. Accurate to whatever degree of integrity you have provided the data for. So this is the realization. This is the contemporary realization, and this is how we're moving forward in time. So let's take a look at this. I just want to put this slide up just to give you a sense of how far we have come in a very short period of time. When I started in the world of geodetic surveying in 1967, when I got drafted into the Army, this was my world. This is what I did. That's not me, but that's what I did. I was an astro observer. To determine a high accuracy horizontal position, latitude, longitude, or a state plane coordinate, UTM coordinate, we oftentimes had to build towers to make our observations, to get up over the trees, the buildings. Well over 100 feet tall sometimes. So our world was making observations from well over 100 feet in the air. And this was time consuming, incredibly time consuming. And other than the federal government, no one had this capacity. You couldn't go out and find some local surveyor that had this kind of capacity to go do the work. GPS changes all of that. If we look at the development of space-based positioning, it happens almost immediately after the launch of Sputnik. Sputnik goes up in '57. The Soviet Union launches it for one purpose and one purpose only, and that was to scare the pants off of us. And it did a great job. It did exactly what it was supposed to do. It had a tiny little broadcaster in it. There wasn't any scientific packages associated with it. It had a little broadcaster because they wanted to make sure we heard it. They wanted us to know we got there first. In fairly short order after that, two gentlemen working at the Johns Hopkins Applied Physics Lab very quickly learned how to determine the orbit of Sputnik. And shortly thereafter, they wrote the seminal paper that said, hey, if we have a satellite in space and we know where it is, we can position ourselves on the ground. Two people that also worked at Johns Hopkins picked up that paper. They were the first to develop this in collaboration with the Navy. This was all done behind closed doors. The Navy developed the transit Doppler system. This is the daddy of GPS as we know it today. Doppler was developed for one purpose and one purpose only. It was to locate nuclear submarines. You have a submarine that's out in the middle of the Pacific or wherever. Without accurate positioning, they might know where they are within a half a mile. With one pass of one Doppler satellite, these were called Oscars. With one pass, they would know where they were within 200 meters. And I guess they sort of figured that if we know where we are within 200 meters and we launch a nuclear missile, close enough. I think that was the point. By 1967, that technology was released to us in the civilian side and was very quickly adopted and used in this community, in the energy community. It was big time. Positioning oil wells offshore, that was really big. So they embraced, early on, space-based positioning technology. The problem with the Doppler system was that no matter how long you sat there, your positional accuracy wasn't going to be much better than about 1 meter. Not bad, though. Not bad. Go anywhere in the world and determine our location to a meter.
Excuse me, did
Yeah.
you have to wait till the satellite came around?
Yeah, the question was, do you have to wait for the satellite to come around? Very much like GPS, but there were only 7 Oscars, so you have to wait for one to come up and pass over you, and then you might have to wait a day and a half to get the next one. to pass close to you. Unlike GPS now, where you go out and you turn on a button and you got like 12 satellites in view. So it was time consuming. You would actually sit on a station for a week. It was not unusual to sit there for a week to get 1 meter. But that was phenomenal. We'd never seen anything like that. 3 other gentlemen started working with the Doppler, led by a gentleman named Brad Parkinson, who was the Air Force advisor to it. And from them, we developed the Global Positioning System. Now, I show you here a picture of the first commercially available GPS receiver, the Micrometer V1000. This is the one we used at the National, one of the ones we used at the National Geodetic Survey. We bought them in 1982 at a cost of $250,000 a piece. This is the antenna, dipole antenna. It's a ground plane. All of this weighs about 25 pounds. This is the receiver. The receiver weighs 175 pounds, and we put it in the back of a Suburban. And you quite literally almost had to have an advanced degree in geodesy to be able to process one vector. And look at where we are today. Quite literally, I joke about it a lot in various presentations, but quite literally, if you have the IQ of a sweat sock, you can press buttons and make this happen. It does not take much. It's become, they're almost giving this stuff away. It's not quite that cheap, mind you, but comparatively speaking, in the earliest days of GPS observations, the National Geodetic Survey performed the first practical GPS survey in 1983, Summit County, Ohio. It was not unusual for us to have to be out at about 3 o'clock in the morning to wait for the 4 satellites that we needed. And today you go out, you turn on a receiver, and you're going to get 8 or 9 instantaneously. Life is quite good. And there are a whole range of ways in which you can use this technology, and obviously don't have time to go into that. I want to take you on hopefully a little trip here as where we're headed. These dates that you see here, these are my dates. Right? You might only find some of these in a textbook. To me, these are the important dates. February of 1978, the United States launches the first GPS satellite. In 2000, President Clinton turns off selective availability, which means now anybody who has a GPS receiver can determine their location at the 95% confidence level within a few meters. On the surveying and mapping side, those of us who were involved in this, that didn't bother us. We were using dual frequency units, and we were getting centimeter level positioning almost from the earliest days. But some big things have started to happen. In 2010, the United States launched the first GPS satellite with active L5. L5 is one of the signals. That's a 3rd civil frequency. We are going to be, as civilians, we are going to be dedicated 3 signals, L1, L2, and L5. There's an L3 and an L4. And for a while I had a security clearance and I knew what those were, and I could tell you what they were, but then we'd have to make you disappear kind of thing. It's all the military stuff. Here's the key. This is going to be brilliant. This is going to be really brilliant. Spring of next year. Actually, it was supposed to have been launched last month. They had bad capacitors, so they pushed it back to spring of next year. Spring of next year, the United States launches the first Block 3 satellite. Life changes. Positioning life changes when that happens. When we have a constellation of Block 3 satellites. Whole new architecture. This is what we're looking at. 2025, you see my question mark? Is that it? I don't know. I don't know if it's 2025. I have no idea. Could be 2022. Could be 2030. Better than 50 centimeters, in fact closer to 10 centimeter real-time control, real-time positioning, no ground control. Your tool is what's sitting in front of everybody here, this. So imagine, just in this country alone, 300 million people with access to 10 centimeter technology and able to share it instantaneously. 95% confidence. That's where we're headed. NGS understands this, they know it's going to happen, so we've created a plan. The idea is to move forward. In addition to GPS, we have to consider the other satellite constellations, GNS, that's Global Navigation Satellite Systems. The Russian GLONASS is already operational. Their biggest problem is they don't have a tracking network on this side of the globe, but they're working on that. The European Galileo, they already have 18 satellites. They'll have 30 by 2019. And we know the Chinese, their system, Beidou, they're going to have 30 by 2020. So roughly 2020, 2021, just a few years from now, 4 different constellations of satellites providing position, timing, and navigation. The capacity for us to achieve a few centimeters instantaneously with no ground control now becomes a reality, or very close to it. So NGS developed a plan, and here's a URL for it. It's a typical governmental plan that if you go read it, you'll be asleep in about 3.5 minutes. Right? Like any governmental institution, you have to write plans every once in a while that says why we're more important than everybody else, and this is what we have to do. But embedded in this plan says we need to replace our national datums, NAD83 and NAVD88, North American Vertical Datum of 1988. They have to go away. They no longer support what we need to do. And the reality of that is that our national coordinate system, NAD83, this is our biggest problem, right here. It's not as geocentric as it could be. In 1978, when we were designing the NAD83, what's this thing going to look like? The United States was the first country in the world to design a national coordinate system that was not based on a survey mark in some farmer's field somewhere. Our old datum, NAD27, literally based off a survey mark in a farmer's field in Kansas. It's still there today. Go visit it. Right? It's like going to Mecca for surveyors. I took my ex-wife there one day. Bad thing, bad thing, bad thing. Don't take it. In 1978, 79, none of us at the National Geodetic Survey could fathom how fast GPS was going to change our life. But we knew the future was going to be space-based. So we said, the origin of our coordinates needs to be at the same origin as the satellites. Well, that's perfectly logical and sensible. But our knowledge, our global knowledge of the location of Earth geocenter, that is, all the measurements we had from all around the world, told us that our knowledge of Earth geocenter, that is, where is it really located, had an uncertainty of about 2.5 meters. Not bad. It's a big planet. And unless you happen to be Jules Verne, you can't go there. Right? So you have to deduce its location. In the intervening slightly more than 30 years, our global knowledge, because of global interactions, data sharing, and improvements in positioning technology, has gone from roughly about 2.5 meters to 3, count them, 3 centimeters, just a little over an inch. Our national coordinate system, NAD83, is still based on that older definition, even though internally we've made multiple changes that allow us to position ourselves within a centimeter or so. From Maine, literally to Guam, we can position ourselves within a centimeter. But we are biased to the best global coordinate system by roughly about 1.5 meters. We have to deal with that, because once our positioning comes strictly from the satellites, now that 1.5 meters will show up with anybody with any resources. We also have issues on the vertical side, and I realize probably not that many of you are critically using vertical. Horizontal is by and large the biggest issue you deal with. But vertically, we have many, many challenges in this country, particularly things such as vertical velocities, uplift and subsidence. It's big across many parts of the country. And we rely currently on those passive marks. We need a better solution for that. And that's being worked on. I'm going to show you that in just a second. I'm almost done. So we have names. We now have names. So NAD83 now actually becomes 4 reference frames, because the United States and and some of our territories exist on 4 different tectonic plates. So we have the North American terrestrial reference frame. That'll cover all of North America, including Canada and Alaska, and we work collaboratively with the Canadians. But the area of the Caribbean, Puerto Rico and the Virgin Islands, the Marianas Plate, Guam and the Northern Marianas, and the Pacific, Hawaii and American Samoa. NAVD88, our national vertical datum, becomes a single height system across the entire scan of the United States, now called the North American Pacific Geopotential Datum. I have no idea who the marketing people were that figured these names out, but they're awful. They're just awful. They do not roll off your tongue, right? I did not have a hand in it, so that's what they are. Right? This is what we will be looking for. The origin, the system that we refine these to, is referred to this, the International Terrestrial Reference Frame. It comes to us from an institution headquartered in Paris. So our knowledge of Earth geocenter, down to a couple of centimeters, how the Earth wobbles on its axis, all the Earth orientation parameters are provided to us through this institution that many organizations around the world share data with. We have colleagues here from Korea, and their national survey institution submits data and is part of this global framework just as we are. And it's from these folks that we get what I commonly refer to as the international gold standard for positioning, and that's this thing called the International Terrestrial Reference Frame, or the ITRF, and the most current one is dated 2014. That's where NGS will migrate to in 2022. And from these folks we get our velocities, our Earth orientation parameters. So I put the question out a few minutes ago, how fast are we moving? Well, here we see North America, and doing this nice little southwestern rotation. If you're from this area, if you're from around Pittsburgh, and you don't like living here, maybe the winters are a little tough for you, you're going to wait about 208 million years, and Pittsburgh's going to be somewhere down around Scottsdale. And it's just doing this nice little rotation. So how do we know this? Where does this come from? Well, here we see it for just North America. Here's one of those continuously tracking stations right here in Pittsburgh. It's run by the Pennsylvania DOT, and here are the velocities. It's moving north about 3 millimeters a year, negative east, so that's west, 1.5 centimeters. So there's your number, 1.5 centimeters. Virtually the entire United States from about, Nevada to Maine is moving about 1.5 centimeters to the southwest. And Pittsburgh actually is subsiding, about 1.5 millimeters a year. So there's that going on as well. And with those old passive marks and systems that are stuck in time, there's no way to utilize positioning technology to its greatest extent. We might as well take those receivers and almost throw them away if we're not going to utilize them to their greatest capabilities. I just put this up just to give you a sense of the kind of data that's available, and I realize if you're not a surveyor, this may not mean much to you. Here's a picture of that station over in Pittsburgh. Here is that global coordinate system, right here, and here are those velocities. This is a data sheet, comes right from the NGS database. Anybody can go and download it. And here's our national coordinate system, NAD83. And if you compare these two positions, you'll find they're different by roughly about 1 meter horizontal and about 1 meter in the ellipsoid height. So these are the changes that need to be made. Ultimately, our national coordinate system will have to go much closer to what this is. So if we look at this roughly 1.5 meters that I talked about, well, it's quite easy to determine its location. Here you see the offset. Here's that station, PAP, right there in Pittsburgh. In an Earth-centered, Earth-fixed X, Y, and Z global coordinate system, we just look at the changes. So here's Earth-centered, Earth-fixed coordinates in our best global system. Here's our national coordinate system. If I simply differentiate those, and I take the square root of the sum of the squares, I get 1.5 meters, 1.6 meters. And that's the average, roughly about the average for the United States. So that's the big push. That's most of what we'll see. On the vertical side, now the collection, the transformation has gone from, and is going from, actual measurements on the ground of height differences, referred to as leveling, which is the best way to go about that. It gives us our best height differences. But it's incredibly expensive, incredibly time consuming. We're now flying airborne gravity across the entire United States, and it's over 60% done right now. The country this program has been monumental in its design of new technologies, and no one else in the world is doing this. The idea being water and other fluids, oil and gas, right, flow with respect to gravity. That's what you really want to know, is what the gravity values are. And we've never really had that because we didn't have the capacity to make those observations. Well, with the development of space-based platforms, GRACE mission, which is 2 satellites, launched by the United States, launched in 2002, still operating, and one from the European Union, GOCE, that came down in 2013. We have now mapped the global gravity field and continue to do it at levels that were inconceivable just 10 or 15 years ago. So by taking this space-based platform, which gives us our broad picture of what the gravity field is doing over the whole Earth, and combining that with terrestrial measurements, very, very high accuracy terrestrial measurements, very, very expensive gravity observations. And some of you in the oil and gas industry, gravity observations have been historic in this community. Not quite to the level that the National Geodetic Survey is doing, but nonetheless, it's been part of the world that the oil and gas industry works in. So now making these terrestrial measurements to a very, very high degree of integrity at strategic locations, looking at the space-based platform and bringing them together with airborne gravity across the entire United States, we now compute the gravity field for the United States. As of the end of last year, it says 58%, but I've talked to the people at NGS. We're well over 60% at this point in time. Where we are here in Pennsylvania, we're kind of down right around here. So this data is being processed literally as we speak, and every year in the summer, so I'm expecting sometime between July and August, NGS will release a new tool that will help us define what positions are going to look like in 2022. So it's quite easy to determine what the positional differences are going to be in whatever community you're worried about, wherever you are in the United States. There's a tool that will allow you to at least determine, to a very high degree of integrity, what those changes are going to be. Not the final values, but very, very close. And just in general, here's what we're going to see. So if we look at least from this diagram, it was produced by the National Geodetic Survey, it looks like most of Pennsylvania is going to be roughly between 1.1 and 1.2 meters. I've done some computations, and actually this kind of needs to get shifted over by 1/10 of a meter. It's going to be closer to about 1 meter. And the same is true with heights. We're going to see considerable height differences, so roughly on the order of almost 1/2 meter height differences in southwest Pennsylvania. I've taken at a presentation I gave for the Pennsylvania Society of Land Surveyors a few months ago, I computed what they were going to be in this general area. So I'll share that with you. But here we are near Pittsburgh. There's a survey mark. It's designated HL18B, and this is called a PID. If you go into the NGS database and you type in that KX2394, you're going to get a data sheet on this survey mark. It's going to give you all the information about it. I took that mark and I projected it into the future with this tool that NGS provides. It's a beta tool that you can use to estimate what changes are going to be, and you can see between Pittsburgh and State College, the difference are almost exact. Roughly about 1 meter horizontal change and 40, 44, 45 centimeter changes in height. So whichever one of these is critical to your needs, you need to be aware of that. And you need to be communicating that to people in your office, maybe the surveyors, the contractors that work for you or with you. You need to be aware of what these changes are going to come about so that as you move forward in time, you're collecting information that will allow you to make these transitions as easily as possible. They will never be easy and they will never be painless. But NGS and others are going to be producing tools that will allow you to do these transformations as quickly as possible. One of the conversations we had at the event last night was this issue, metadata. Tell me how good your data really is. And this is a common theme that I've heard over and over and over and over again from people all around the country. And not just in the GIS community, but everybody. And I'm almost done. What data are you working on? How accurate is your data really? Mike Tully gave a presentation yesterday. I'm sorry I missed that. He was talking about how accurate is your data. Not the number of digits to the right of the decimal point. It's critical to have the metadata that, A, if you have surveyors or others who are collecting that data, that they produce, that they give, and if you are accessing data from others, make sure that metadata is coming along with it. Otherwise, it's worthless. It's worthless. This is it. Heights and positions without appropriate metadata is the same as a boundary in Google Earth. Pretty much this. It's just a guess. Right? So this is critical in our world. Let me give you a couple of very quick examples, and I'll finish off here. Here are some, what I think are excellent examples of really, really bad metadata. This one happens to come from a surveyor's plat. It says concrete bound, so I know right away that's up in New England. They call everything a bound. And it gives it a height, 73.68. Well, first of all, is that meters or feet? I'm pretty sure it's feet, because almost nobody works in meters here. GPS datum. Ooh, okay, what the heck is that? I have no idea what that means. This one I particularly love. This is relatively recent. The Supreme Court of the United States, and that just kind of grabs you right off. It's the boundary between the United States and California, the 3-mile offshore boundary. So this comes directly from the Supreme Court. Here are the coordinates for various points, 3 miles offshore, in UTM coordinates in meters. Okay, no problem there. Notice they're shown to the nearest millimeter. 3 miles offshore. Okay, I'm sitting out in the water. How close can I come to a millimeter? Fair enough. It shows 2 datums. NAD83, our national datum, and WGS84, World Geodetic System 1984, which is the default coordinate system for the global positioning system. And I suspect that there are quite a number of you in this room that have data in your databases, or that people give you, or maybe you acquire and send to somebody else, and you say, oh, it's WGS84, and it's accurate to a few centimeters. There's no such thing. It does not exist unless you're in the military. WGS84 is a purely military-driven system. You cannot get centimeter-level coordinates in WGS84. So if you had any of that, go back and look at your data. You do not have centimeter accuracy in WGS84. These 2 datums are different by that 1.5 meters that I showed you. So I have it says 2 datums, which are different by 1.5 meters, yet they show the coordinates to the nearest millimeter. When I first saw this, my first thought was, Sonia Sotomayor is sitting up late at night computing UTM coordinates, and I'm in love. I'm thinking, I want to go love this woman. She's computing coordinates at night. This is great. Of course she doesn't. Of course she doesn't. Obviously none of them do that. They get it from some federal agency, and we chastise them severely for it. One last one, and I'll be done. Just to give you an example of how prevalent it is for bad metadata. I found this on an NGS data sheet. This comes right from a piece of an NGS data sheet. These values you see over here, LE000, that's that PID I talked about earlier. It's not a real number here. I've taken it out so when I show this somewhere, nobody can figure out who the knucklehead was that submitted this thing or where it is. But this is provided by a surveyor. So the surveyor goes to the field. He happens to be in Iowa, so Mike Tully's back here, he's from Iowa. This happens to be a surveyor in Iowa. He goes out, he finds this survey mark, he occupies it with a GPS receiver, he submits the report, so that's a good thing. He says, yeah, I found the mark. And then he provides his own information to say, hey, this is how close I measured to what the National Geodetic Survey provided. And I want to show you this, because it's probably not easy to see from where you are. But here is his latitude and longitude that he provided. Degree north, 30x, so I took that out, 50 minutes, 55.1820478 seconds. 8 decimal places in arc seconds. Do you have any idea what a change of 1 in the 8th decimal place of an arc second is? It's less than the width of a human hair. So this guy is saying, hey, I got a measurement and it's better than anything on the planet that anybody else can get. So right away I know this person is clueless about metadata. So just another bad example. And I could go on and on and on. I could spend 8 hours up here yapping at you about this stuff. But I just wanted to give you a taste of what the National Spatial Reference System is, what these changes are going to be about. They are going to be large. Even though the shift is not significantly large, a meter horizontal, it's going to have a big impact on much of what many of you do. So the whole point of me here is to say, be prepared. There's information out there. Be prepared. Start to understand what's going to happen and be able to communicate that with your colleagues and people in your community. So I always end with good coordination begins with good coordinates, and geography without geodesy is a felony in my world. Again, just an introduction to what's going to be happening positioning-wise for all of you in the near future. I look out at the group of people here, and with only a few exceptions, most of you are, comparatively speaking, young. I'm envious. I'm not envious you're young, because I'm retired. I get to sit there in the morning when you're going to work and it's snowing, I'm having my cup of coffee going, have a nice day. I'm envious because what you're going to have in front of you, positioning-wise, the capacity of dealing with spatial informations rapidly, and the impact that they can have on your community is something I don't think anybody in here can even grasp yet. And just listening to some of the presentations yesterday, I could hear how some of you struggled with management levels. Well, that's probably going to get worse. So I can't give you something there. But boy, what's going to be in front of you, the capacity for you to collect, share, and modernize the spatial reference frame of the entire United States for the multitudes of things that we all do is phenomenal. I can't say it hard enough. I thank you very, very much for this opportunity to be here today. I wish you could have been here for all the sessions yesterday, but just in listening to what was going on last night, it sounded like it was a terrific day, and looks like from the program you have, it's going to be a terrific day today. So I thank Mark and Harold for the hospitality here, and I greatly appreciate the time. Thank you very much.
We have, don't wander off, Dave. At this time, we would like to thank you for the effort of coming into Pittsburgh and sharing your time with us, and we'd like to give you that.
Cool.
And thank you again. Okay. Got it, Linda?
Hold on. Technical difficulty
There
there.
we go. Don't worry, we have plenty of those.
Yeah. There we go.
Good?
Thank you.
Okay, thank you.
Thank you.
Thank you for your time.
Oh,
And
my
you're
pleasure.
going to be here through the break?
Yeah, I'll be here through the break. If I could make one recommendation for this conference next year, do it when the Pirates are in town. That was the one thing that I did not like about coming here. I was excited when I got the email from Mark. I'm a big baseball fan. I'm a Baltimore Orioles fan. And I thought, no, I've never been to Pittsburgh to see a game. I'm going to Pittsburgh to see a game. The Pirates are playing in Baltimore tonight. I might as well go home. Thank you.